And we can get going. So welcome everyone. We're delighted to have another Vinberg Distinguished Lecture today. Today's speaker is Professor Richard Borcherds of UC Berkeley. He received his PhD under John Conway from Cambridge in 1985. He's a recipient of many awards and honors, including a 1992 EMS Prize, a 94 invited ICM lecture in Zurich. Same year, he was elected Fellow of the Royal Society, a 1998 Fields Medal, 2012 was Fellow of the AMS, 2014 member of the National Academy of Sciences, many, many other awards and honors, and I'll be here all day discussing them if I don't get out of his way. So the title for today's talk is Vinberg's Algorithm and Kac-Moody algebras. Please take it away.
Okay, thanks. So this talk is going to be about Vinberg's algorithm for finding calculating the reflection group of a Lorentzian lattice. I'm going to focus in particular on one example in 25-dimensional hyperbolic space, which was found by John Conway many years ago, which turns out to be related to a certain Lie algebra and an automorphic form. And then I want to show how John Conway's example can kind of be and John Conway and Niels Sloan discovered that this example can kind of be used to explain many of the examples found by Vinberg in lower dimensions. So I'll start with Vinberg's paper, and let me just try and share the screen. Okay, I hope this is now showing a piece of paper. So Vinberg's, I found it while browsing in this book. And Vinberg has this paper on some Lobachevsky spaces, which is, of course, the same thing as hyperbolic space. And in this paper, there are these really intriguing diagrams. I mean, up here, we've got the usual Coxeter diagrams of reflection groups, which everybody's probably seen. But down here, we find these rather strange extra diagrams. And there are some more here. You see there are these rather mysterious looking things that aren't quite circles. And, I sort of really wanted to understand what on earth these diagrams are. I mean, somehow the idea of doing deep mathematics just by doing little doodles on a piece of paper has always rather attracted me. So how does this work? These are just Dynkin diagrams or Coxeter diagrams of hyperbolic reflection groups. So what I'm going to do first is I'm just going to start by having a quick review of reflection groups. So a typical reflection group is generated by certain reflections in, well, you might start with Euclidean space. So here we might have three mirrors, and by repeatedly reflecting in these mirrors, you see we've got a reflection group with 6 elements. And the mirrors divide space up into regions, so each region is called a fundamental domain. And if you pick one fundamental domain, so you might pick this one here, then this fundamental domain has 2 walls, so this wall, and these are called the simple roots. And Coxeter found a very simple way of drawing pictures of reflection groups. You draw a point for each simple root, and you draw lines between the points indicating what the angle between these is. So if there's an angle of pi over 3 between the 2 walls, as there is here, you draw a single line between them. So this reflection group is drawn by this rather simple Coxeter diagram. Another example might be you just take 2 orthogonal hyperplanes. So this reflection group is order 4, and this time the angle between them is pi over 2, and for that you don't draw any line between them. there's a slight technical difference between Coxeter diagrams and Dinkin diagrams. So Coxeter diagrams and Dinkin diagrams are almost the same thing. The difference is that Dinkin diagrams add information about the length of a vector perpendicular to the hyperplane. So you can indicate a hyperplane by choosing a vector orthogonal to it. And the Coxeter diagram doesn't care about the length of this vector. In the Dinkin diagram, you put a little bit of extra information saying what the length of this vector is. Furthermore, these vectors have and there are some reflection groups where you can't make these vectors lie in a lattice. For instance, if you take the D10 reflection group with 10 elements, then the reflection, and you take the vectors orthogonal to these, then you can't make them lie inside a nice lattice at all. So most of the time, Coxeter diagrams and Dinkin diagrams are essentially the same thing, but there are these subtle differences. And you remember there are three sorts of geometry that you come across, which are spherical geometry with positive curvature, Euclidean geometry, and hyperbolic geometry. And each of these three cases you can consider the different sorts of reflection groups. So spherical reflection groups, the ones that everybody comes across first when they do reflection groups, except you sometimes don't notice they're spherical because you embed the sphere in Euclidean space. There are some pictures of spherical reflection groups drawn in the plane in this book by Klein and Fricker on elliptic modular functions. This has recently been republished as an English translation, if anybody has trouble reading the German. So here are some more rather fine examples of reflection groups. So this is actually the icosahedral reflection group. It's all the symmetries of an icosahedron. It's one of the ones that doesn't have a Dinkin diagram because you can't make the roots into a lattice, and you can even make three-dimensional models of it which kind of look a bit like this. So the spherical reflection groups are just classified by the usual AN, BN, CN, DN, E6, E7, E8, F4, and G2, except there are also some other ones, I2, H3, and H4. So this is the icosahedral group, and these are ones that don't correspond to Dinkin diagrams. So for pictures of them, well, I sort of showed you pictures of them in Vinberg's paper, so I'll just do that instead of drawing them all out again. So here's a list of the Coxeter diagrams of the spherical reflection groups. Next, you can look at Euclidean reflection groups, and a typical example of these might be one where you take a lot of equilateral triangles like this. So here, the fundamental domain is going to be this region here, and you can see it has three simple roots, and the angles between them are pi/3, so its Coxeter diagram just looks like this. It's a bit of a coincidence that this Coxeter diagram happens to be the same shape as the fundamental domain in this case. And the classification of Euclidean diagrams is pretty close to the classification of spherical ones. For example, if you take a Euclidean diagram and fix one point of the fundamental domain, you can see there's a little sphere or circle around that point, and you're getting a spherical Dinkin diagram from that. And this gives you a correspondence between spherical and Euclidean diagrams that isn't quite one-to-one. You sometimes get two Euclidean diagrams corresponding to the same spherical ones. But anyway, Vinberg's paper also contains the all the Coxeter diagrams of the Euclidean reflection groups, and you can see that they look rather similar to the spherical ones, except you kind of add 1 point. So if I take AN here, it's just a line. And to get the corresponding Euclidean one, it turns out you add an extra point joined to the 2 endpoints. So if, the example I gave was if the line has just 2 points, then the corresponding Euclidean one has 3 points, so it's a little triangle.
I'm sorry, weren't all of these for the spherical and Euclidean, this was already worked out by Coxeter himself. Is that
yes. Right? Yeah. This goes back a century to Coxeter, who I'm not actually quite sure whether Coxeter did the Euclidean ones or not, but he sort of knew about them. And what we're going to be doing is looking at reflection groups of lattices in well, we might start with lattices in Euclidean space. So an obvious lattice in Euclidean space is just a copy of is just all points with integer coordinates. So it's a copy of n products of z contained in n products of r. So you can think of these as all the vectors m1 up to mn with mi in the integers. And what we want to do is to find the possible roots such that if you map a vector v to reflection in the orthogonal complement of R, then it maps Cn to z to the n. And you can see that this happens if R has norm 1 or 2, because we're taking v to v minus 2 vr over r times r, and you want this thing here to be an integer most of the time. So if this is at most 2, then this factor here will be an integer.
I'm sorry, Richard. May I interrupt you for a quick question that popped up on the chat?
Yeah.
So I think I'm going to ask it for Christopher. Is there any relation between the non-solvability of the quintic and the fact that you cannot place the root vectors on a lattice? For example, those that correspond to the polar lines of the vertices of the icosahedron.
I don't know of one off the top of my head, but it wouldn't be surprised if there was one. I mean, you could read through Klein's book on the icosahedron, which is talking about both of these things, and there's quite possibly some relation, but as I said, I can't offhand think of one.
Thank you.
Anyway, so let's just work out what the Coxeter diagram of z to the n is. So all the roots are going to be either things of the form 0, 0, 1, 0, 0, 0, or I guess there could be a plus or minus 1, or 0, plus or minus 1, plus or minus 1, 0. So it's allowed 1 or 2 ones there. And you can find a set of simple roots for a typical fundamental domain. It might look something like this. You get minus 1, 1, 0, 0, minus 1, 1, 0, all the way up to 0, minus 1, 1. And then you could also add in this vector 1, 0. And this vector is norm 1, and these all of norm 2. And if you work out the Coxeter diagram, sort of put a double in here and put an arrow on it in order to indicate which of these vectors is smaller. You can think of the arrow as being a sort of inequality sign. So this vector is smaller norm than this. So that's one example that's going to come up a bit. Another famous example of a lattice is the E8 lattice, which consists of all vectors m1 up to m8, such that mi are all in z, or all the mi are in z plus a half, and the sum of the mi is even. So for example, as well as the vectors of the form with 2 plus or minus 1s in them and lots of zeros. We can also get vectors with plus or minus a half, all the way up to plus or minus a half. And you can see there are 128 of these vectors and 112 of these vectors. So altogether you get 240 roots. And if you work out the Coxeter diagram, it looks like this. The very famous E8 Dinkin diagram. And you can write down some roots explicitly if you like. So you can start by saying this one is minus 1, 1, 0, and so on. And this one is 0, minus 1, 1, 0. And I'm not going to write out all the rest because it's not terribly interesting watching somebody do this. This corresponds to a certain Euclidean reflection group, and the Euclidean reflection group has a Coxeter diagram that looks like the E8 reflection group, except you add in one extra point. This reflection group kind of lives in Euclidean space and includes not only all the reflections of the spherical E8, but a whole lot of translations corresponding to vectors of the E8 lattice. I think I forgot. Here are Klein and Fricker's pictures of a few Euclidean reflection groups in the plane. So what I'm going to talk mostly about is hyperbolic reflection groups. So let me just give some examples. Well, first of all, anyone who's done modular forms has come across the hyperbolic reflection group GL2 of Z. So this is just 2 by 2 matrices with coefficients in the integers with AD minus BC equals plus or minus 1. And you know this acts on the upper half plane in the usual way by looking like this. And if you work it out, you find the reflection hyperplanes kind of look like this. So there's first of all, you can reflect in vertical lines. So this is the point. So these are the vertical lines correspond points a half, 0, minus a half. And then you can also kind of reflect in this circle here. This is essentially tau goes to minus 1 over tau. And a fundamental domain of the region looks like this. This is half the size you may be used to if you've done modular forms. That's because I'm taking GL2 rather than SL2 to get a reflection group. And we can work out the Coxeter diagram of this because there are 3 walls to the mental domain. So we get 3 points. And then we have to join them depending on what the angles are. Well, here we've got an angle of pi over 2, so we don't join them. And here we've got an angle of pi over 3, so we draw a, let me do this the other way around. Let's make, see, these ones not joined, so that's pi over 2. And here there's an angle of pi over 3, so those two are joined. And then these two kind of meet at infinity, and you indicate that by, well, there's no really standard notation, but people sometimes draw a really big solid line. Or sometimes they draw a double line. It's all a bit confusing. So this is the Coxeter diagram of this hyperbolic reflection group.
Sorry, can I ask, GL2 will take the upper, if you have determinant minus 1, it takes the upper half plane to the lower half plane. But you mean if you have complex conjugation, then you can...
Yes. This would be if AD minus BC is plus 1. If AD minus BC is minus 1, then you should complex conjugate this. So I'll sort of put a complex conjugate as kind of optional. And there's some other reflection groups, sort of new Coxeter, and use hyperbolic reflection groups in some of his pictures. So this sort of fish picture is actually a picture of a hyperbolic reflection group. You can see these reflection hyperplanes as kind of white lines going through the picture. It looks as if it's getting really hot and tiny near the edge here, but that's because when you embed hyperbolic space in Euclidean space, you have to distort, and it's not really getting cramped up there. It's a picture of a hyperbolic space. The lines of these going through the picture. See what comes after Escher. For spherical and Euclidean spaces, you can pretty much classify all the reflection groups in huge, even in dimension 2, and in dimension 3 and above, it seems to be very hard to classify them. Well, there's one obvious example of hyperbolic reflection groups, and this is if you take a Lorentzian lattice. So this is a lattice L contained in Rn, 1. So the quadratic form is x1 squared plus x squared minus squared. So you notice you've got this Lorentzian, because this is, of course, the space that physicists use when doing special relativity. There's actually a huge divide between people who write this as Rn, 1 and R1, n, so whether it should be mostly negative or mostly positive. I'm going to use this convention because it's easier at the start, because this ties up with positive definite lattices, but there are rather strong reasons for using the other convention. And the point about this is we can find a model for hyperbolic space as follows. If we look at the vectors with v equals -1, then, well, the vectors with v of norm 0 form a kind of double cone. It's the light cone from special relativity. And the vectors with v equals -1 form a sort of hyperboloid of 2 sheets. And each of these sheets is isomorphic to a copy of n-dimensional hyperbolic space. And furthermore, the group of rotations in Lorentzian space is up to a factor of 2 or so, the same as the group of symmetries of hyperbolic space. And we can now get lots of reflection groups by taking a vector r here, preferably with r squared equals 1 or 2. And then if we take the hyperplane orthogonal to this and reflect it, we get a reflection group in hyperbolic space. This gives you a big supply of hyperbolic reflection groups. And the question Vinberg looked at first was find the Coxeter diagrams of this lattice here, or possibly this lattice here. So what is this? Well, this is just points x1 to xn in Lorentzian space with all the xi integers. So it's the simplest possibility you could have. This is kind of similar, except you do the same trick we did for E8. So this one, you take xi are all in Z, or they're all in Z plus a half, and the sum of the xi is even. The nice thing about this is if n, we usually take n congruent to 1 modulo 8, and this will then be an even lattice. This means that r squared is always even rather than just any integer. So these are both unimodular lattices. That means the volume of a fundamental domain is just 1. And in fact, optoisomorphism, they're the only unimodular lattices in Lorentzian space. So the problem is find the reflection groups of these lattices. And for this, he introduced Vinberg's algorithm.
Sorry, we couldn't see the very bottom of that last page.
Okay, let's have a look. Oh, okay, yeah.
The last line was cut off, that's all.
Yeah,
yeah great.
I'd better avoid the bottom. Yeah, the Zoom camera size is a bit different from what I'm used to. So here we have Vinberg's algorithm. And what Vinberg's algorithm will do is it will take you a hyperbolic reflection group, and if you're lucky, it will tell you what its Coxeter diagram. Am I audible at the moment? I've just had a little error message pop up on screen. So can people hear me?
Yes.
Yes, I think
I'm
we
getting
can.
no response. Oh, you can hear. Okay, sorry, I just had a thing saying my connection's gone down. So it works as follows. What you do is you take hyperbolic space. I'm going to draw hyperbolic space as a kind let's take some hyperplanes. So it might look something like this. And suppose this is a fundamental domain of the reflection group. What you do is you pick any point inside of the fundamental domain, a special point P, and the idea is very simple. We find the reflection hyperplanes in order of the distance from point P. And the key point is the angle is always less than root of pi over 2. So you first find the first hyperplane, then the second one, and so on. And each time you find some hyperplanes, this puts constraints on the later hyperplanes you're looking for, because the internal angle will always be less than or equal to pi over 2. So actually this one wouldn't really work because the angle there is less than pi over 2. So I ought to have a fundamental domain looking like that. So that's a very simple idea. And if you implement it, for lattices, picking a point P corresponds to pick.
Sorry, essentially it says that two faces intersect, right? Like since angle is smaller than pi over 2, that's because all angles are smaller than pi over 2.
Well, if the angle exists, the faces in hyperbolic space that the reflection hyperplanes might not even intersect at all. I mean, they might intersect only at infinity, or they might even at infinity. And this is actually rather a nuisance because there is no good convention for drawing Coxeter diagrams when this happens. So people kind of fudge things a bit.
Yeah, and since
picking a point P means we pick
another thing. Sorry, the example you just that was right before, it was not co-compact action, right?
Which
the
example?
Reflection
This
group you
one?
Constructed right before.
GL2.
Which, oh yeah. Not, but does have finite volume. So for Euclidean and spherical reflection groups, you're mostly only when the fundamental domain is compact. For hyperbolic reflection groups, that there are some compact examples, but many of the examples may be non-compact but still have finite volume. And there are also actually some interesting examples that don't even have finite volume. In fact, we will see Conway's example of this a bit later on. So picking a point P means you just pick a vector V with V squared less than 0. So in terms of the picture I had earlier, so we have hyperbolic space kind of lives here. And what we're doing is P is going to be some sort of vector here that lie in the point of hyperbolic space. And the reflection hyperplanes correspond to vectors R. Typical vector R might be like this, with R squared greater than 0, and we usually want R squared equal 1 or 2 if the lattice is unimodular. There are more complicated cases when R squared is norm bigger than 2, but we won't worry about those. And what we do is we pick them in order of the distance of this point V from the reflection hyperplane R, and that turns out to be taking them in order of, well, you first of all normalize R so that it is length 1, and then you just look at the inner product with this vector V. And the inner product isn't actually the distance, but it's sort of an increasing function of the distance. So what we're going to do is to find the vectors R in order of this distance here. So let's see what happened. So we're going to look at I n 1. So this is all vectors m1 up to mn, n plus 1. I'll usually try and put a vertical line here to remind you that this coordinate has a sort of negative norm. All these coordinates are positive norm. So let's look at the first few cases. So n equals 2 what we do is we first of all start off with in contained in in comma 1, and we can start by taking all the simple roots of in. So we sort of get these vectors 1, minus 1, 1, 0, minus 1, 1, and so on. So this gives us a Dinkin diagram, and what we're doing is we're sort of picking. We have to pick a vector p, and we take p to be the vector 0, 0, 1. So what we have to do first is to start with all the planes at distance 0 from p, which are just giving us a set of simple roots for in, which is the Bn Dinkin diagram. So it sort of starts off like this. And then for n equals 2, we get just one extra point, 1, 1, 1. And this vector has norm 1. Sorry, I've got my signs muddled up a bit. I think that should be minus 1, and these should all be plus 1, minus 1. So I want this to have inner product at most 0 with that. And this gives you Vinberg's first diagram, which just looks like this one here. See here, the first 2 points of the Bn Dinkin diagram, and then we add this one extra point. And then for n equals 3, this check we sort of lose this vector, and we get the vector 1, 1, 1, 1. And this gives us this diagram here. And this is norm 2, and is actually stable in the sense that no matter how much you increase n, we always get a vector a bit like it, which looks like this. This one wasn't from n equals 3, it sort of gets killed or replaced by a vector of norm 2. But once you've got a vector of norm 2, they tend to be stable. When you go up to, nothing much happens until you get up to about n equals 10. So here he has the vectors with n up to 9, where you're just sort of adding one extra. Here you've got the Bn Dinkin diagram with this one extra vector, which is this vector here. And at n equals 10, we get a new root, which looks like this. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3. And you see this again has norm equal to 1. And what you notice here is the number of simple roots is now bigger than the dimension of the lattice. So the simple roots are no longer linearly independent. And you see, this is now this diagram here. So we've now got the BN diagram, which is this bit here. And we've got the two extra roots we have. So this root here is this one that I wrote down. And again, this one is not stable. For n equals 11, it becomes this root 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 3 of norm 2. And this root is now stable. We get it. We get the same thing with a few zeros at the front, no matter how much you increase things. And for n equals 12 and 13, again, nothing much happens. For n equals 14, we get a new root. And this time we get 1. I'm losing count of the number of ones, but now you get a 2 and then a 4. And this is norm 1. Diagram now looks like this. What you notice is the Dinkin diagram has now acquired a symmetry of order 2. So the new phenomenon here is that we get a symmetry of the Dinkin diagram. So the Dinkin diagram is becoming more symmetric. And what happens as n increases, well, you can see what's going to happen. Things are going to get increasingly complicated because as we have more coordinates here, we have more room to think of simple roots, and we're going to get more and more complicated sorts of roots coming up. Moreover, the symmetry now tends to increase with n. Here's what you get when you let n equals 15 and n equals 16. You see the symmetry has now increased more. I think this is a symmetry group of order 4 instead of 2. And here the symmetry group has increased further, so it's now of order 8. So for n14 up to 17, the symmetry group is increasing. For n equals 18 and 19, we get a rather odd thing going on, is that there are now 3 types of simple roots. And you may think there are 2 obvious types because it can have norm 1 or it can have norm 2. So what's the third type of root? Well, there's an extra thing roots can do, because a root can have the special property. So root R can have the property.
I'm sorry.
So what's happening?
Can I ask you a question?
Yeah.
Your algorithm, Vinberg's algorithm, enumerates the vertices of the Coxeter diagram according to a certain order, right?
Yes.
And what are the possible orders depending on the starting point? Will it always enumerate the vertices of the diagram? So it's going to be connected each time, but it's not clear. Like, can you add vertices on the left, on the right, or will it always be starting at an endpoint?
You can choose the point inside the fundamental domain so it's nearest to any one of the so the order can vary a lot depending on on which point inside the fundamental domain you choose. What you usually try and do is to choose a point that lies on as many reflection hyperplanes as possible, since then you've got all these hyperplanes to less work to do. So you'll normally choose a point that lies on so that the roots orthogonal to it form a large Euclidean or spherical Dinkin diagram.
But in that case, the algorithm may lead to making choices. Like maybe at some step you've got two choices between the new reflection to add.
Yes. There may be more. There may be more than one. There may be more than one reflection distance point. In fact, we'll see in a moment there can be a number of simple roots all at the same distance. For that, you just add the whole lot. So the exact order doesn't matter to you. You just add all the roots at each distance. So the root R can have the following property. It can have the property that RV is congruent to V squared mod 2. For example, if you take the root 1, so there are 18 of these, and 1. So this root now has norm 1, and you notice that this is the property that RV is congruent to V mod 2 for all V. So some roots will have this funny property here, sort of fundamental roots of the same norm. And this first happens notably here, n equals 10 and 19. It tends to happen whenever n is congruent to 2 or 3 modulo 8. So for n equals 2 mod 8, we'll get norm 1 roots, funny property, and for n equals 3, we get 2 roots. What happens for n bigger than about 18 or 19, you find the symmetries of the Dinkin diagram, it's almost transitive on the simple roots, except for two things. It can't move a root of norm 1 to a root of norm 2, and it can't move a root that has this property to a root that doesn't. So from now on, we'll usually find there are 3 different orbits of simple roots on the Dinkin diagram. For n equals 20, there's a dramatic change. The big change here is that we now get an infinite number of simple roots. This means that Vinberg's algorithm doesn't actually terminate, it just sort of goes on forever. The symmetry group of the Dinkin diagram is also infinite and fairly complicated, as we will see in a moment. The question is, why does it become infinite? And the reason Vinberg found is there are lattices in dimension 19 with determinant equal to 1, such that the root system has rank less than 19. In fact, there are 2 such lattices. The root system can either be A11 D7 or it can be E6 cubed. There are 2 possibilities. And the point is that this lattice is actually orthogonal to a vector V with V squared equals -1. And by looking at this, Vinberg was able to show that if you take the lattice modulo its reflection sublattice, this actually acts as a group of symmetries on the Dinkin diagram. And so if the rank of the root system is less than dimension, a symmetry group Z acting on the root system. So the symmetry group is infinite, and there must be an infinite number of simple roots. So we can ask, why does Vinberg algorithm break down when you go from n equals 19 to n equals 20? And one reason is that you suddenly start getting unimodular lattices with less roots than you expect. The other question is, why do you get lattices with less roots than you expected n equals 18 or n equals 20? And I'll talk about this in a little bit. You can also do the same thing for the even unimodular lattices. So there are two even unimodular lattices in dimension less than what we've got up to, which are these two here. And the Cox diagrams of these look like the following. What you do is you take 1, 2, 3, 4, 5, 6, 7, 8. You take the E8 Dinkin diagram, and then you add one extra point to get the affine E8 Dinkin diagram, and then you add yet another point, and this gives you the Cox group for this lattice here. And the 18-dimensional one, you do something similar, except this time you take copies of E8, then you take 2 copies of E8, and then you join them together with one extra point. And if you look at these, there's actually a lot of stuff going on here. It turns out that if you take an even unimodular lattice in dimension 8 or 16, it corresponds to a norm 0 vector in one of these lattices here. If you take the orthogonal complement of the norm 0 vector, it's more or less this lattice here up to some null vectors. And this means that the Dinkin diagram of any even unimodular lattice in these dimensions is actually contained in this diagram here. For instance, for I91, you can see that there's one even unimodular lattice in dimension 8, and you can see its affine Dinkin diagram if you put your finger over this point here. In 16 dimensions, there's an obvious even unimodular lattice, which is E8 squared, and you can see its affine Dinkin diagram by putting your finger over this point here. But you can also put your finger over these 2 points here, and you notice that what you've got here, this is just the Euclidean Dinkin diagram of the D16 lattice. So we find there are 2 even unimodular lattices in dimension 16 with root systems E8 squared and D16. The root lattice D16 isn't quite unimodular, but you can make it a bit bigger to make it unimodular. So this is very nice. You can sort of classify unimodular lattices in dimension 16 just by applying Vinberg's algorithm and then just sort of staring at it and finding the Euclidean subdiagrams of it. And you can ask, can you use to classify unimodular lattices in other dimensions? And the answer is you can't really. The problem is that the Dinkin diagram produced by Vinberg's algorithm is just too complicated. I mean, you know, in n equals 20, the Dinkin diagram is already infinite. So, you know, it takes an infinite amount of time to write it down and pick out all its affine subdiagrams. And again, if you look at II25(1), then there are an infinite number of roots, and the symmetry group is infinite for much the same reason we had for the odd unimodular lattice. So the point is that there's a lattice in R24 with root system of rank less than 24. And this is enough to show that the symmetry group of this is infinite. In fact, there's a unique lattice with this property, which is the Leech lattice. And its root system doesn't just have rank less than 24, its root system actually ranks 0. So it fails in a rather drastic to have a root system of rank 24. So the existence of the Leech lattice shows that the Dinkin diagram in this case is infinite. We see that the norm 0 vectors of this lattice here correspond to 24-dimensional even unimodular lattices. And the correspondence is as follows. Suppose we've got a norm 0 vector here. What we can do is we can take the orthogonal complement of W, and this because it's W has norm 0, and this is a 24-dimensional lattice, which you can easily check is even and unimodular. On the other hand, if you've got an even unimodular lattice L, then you can take the direct sum of a little lattice with these inner products, and this is actually isomorphic to the even 26-dimensional unimodular Lorentzian lattice, because there is only one such lattice. And here we can, if we take coordinates to be of the form lambda mn, where lambda is in L and m and n integers, then we can take our vector W to be 0, 0, 1. So norm 0 vectors of this lattice kind of correspond to 24-dimensional even unimodular lattices. And as I said, they also correspond to Euclidean subdiagrams of the reflection group of this lattice. Incidentally, you can use this to construct all the even unimodular lattices. These are, of course, called the Nemai lattices. And there are 24 of them. And yeah, a question that goes
We seem to have lost the speaker. Just give it a minute.
Yes, it looks like.
Sorry.
Okay, you're back. We lost you for a minute there.
Okay. Can you hear me and see me now?
Yes, you were just describing the Nemar lattices.
Okay. So Conway and Sloan pointed out that you can actually construct the Nemai lattices explicitly by writing down a norm 0 vector. And the obvious question is, can you find a suitable norm 0 vector for the Leech lattice? And the answer they found was this one here. So first of all, you take the sum of all the numbers from 0 to 24, and then you take 70. And these integers all have to be different, because otherwise, I mean, if two of them were the same, then you would get a root 1 minus 1 perpendicular to it, which you don't want. So this is the sort of minimum possibility for the Leech lattice. And you notice that 0 squared plus 1 squared plus 24 squared equals 70 squared. So if this vector is W, then W perp over W is the Leech lattice. So this is a very simple construction of the Leech lattice. There's a slight catch. It's actually rather difficult to prove that the orthogonal complement of this vector doesn't have any vectors of norm 2, but anyway. Next, we come to an apparently unrelated Conway, Parker, and Sloan started looking at the covering radius of the Leech lattice. we can ask, what is the maximal distance of a point of R24 from a point of the Leech lattice lambda? And the points at maximal distance are called holes or deep holes or something. Parker came up with this rather extraordinary observation. There were 2 or 3 examples of deep holes known, and he noticed that the deep holes seem to be related to 2 Nemi lattices, A1 to the 24 and A2 to the 12. And inspired by this, Conway and Sloan found all the deep holes of the Leech lattice, and what they found was the covering radius is the square root of 2. And there are 23 orbits of deep holes. And these turn out to correspond to the 23 Nemi lattices other than the Leech lattice. And the way they correspond as follows is you take the Euclidean Dinkin diagram for the Leech lattice. So for the Nemi lattice. So a typical Nemi lattice might be, say, E8 cubed. So let's take the Dinkin diagram for E8 cubed, which looks like this. You take 3 copies of E8, and then you add in 3 extra points. And you can now get a configuration of vectors of the Leech lattice as follows. So each of these points corresponds to a vector of the Leech lattice. And if you've got points V, W not joined, this means V minus W squared equals 4. And if they're joined by a single line, this means V minus W squared equals 6. And you can take a configuration of vectors like that, and it turns out the center of this configuration is then the deep hole. So we've got this completely and absolutely bizarre correspondence between the Nemi lattices and deep holes in the Leech lattice. Turns out there's a sort of explanation for this using the 26-dimensional Lorentzian lattice. What you do is if you take a vector W squared equals 0 with W perp over W equals a Nemi lattice, then you can look at the then we can look at W contained in the lattice II25(1) and look at the roots of II25(1). The roots are with R orthogonal to W. And you see, this will give us a simple root system that, so this will give us a collection of simple roots giving a Dinkin diagram. It's just the Euclidean Dinkin diagram of this Nemi lattice. So the Euclidean Dinkin diagram of any Nemi lattice actually appears in the Dinkin diagram of this lattice here. And Conway took this further and found this amazing description of the Dinkin diagram of II25(1). So Vinberg showed that this Dinkin diagram was infinite. But Conway managed to actually describe it explicitly in this very simple form. The Dinkin diagram of II25(1) is the Leech lattice. And this doesn't even seem to make sense at first. I mean, the Dinkin diagram is some sort of diagram like this with lots of points connected by lines and so on. And the Leech lattice is a subset of R to the 24. So what on earth do you mean by saying that the Dinkin diagram is the Leech lattice? Well, more precisely, I mean it is isometric to the Leech lattice. So it's the same as the Leech lattice if you think of these both as being metric spaces. It's obvious how the Leech lattice is a metric space. a Dinkin diagram is a metric space because you can just take the metric space consisting of the simple roots. So more precisely, it looks as follows. What we're going to do is we're going to apply Vinberg's algorithm to the 26-dimensional Lorentzian lattice. And we're going to write this as the Leech lattice plus this little 2-dimensional hyperbolic lattice. So its vectors are going to be of the form lambda mn, with lambda in the Leech lattice and m and n integers. And the norm is just going to be lambda squared minus 2mn. I'm putting in a minus sign here for no particularly good reason. And we're going to take our controlling vector, which I'm going to write as rho, to be 0, 0, 1. So rho perp over rho is the Leech lattice. And now we're going to apply Vinberg's algorithm to this. And the first batch of roots we're going to take to have r rho should be equal to 0. And there are none here because the Leech lattice has no roots. Now we take r rho equals 1. And now we get roots which look like lambda 1, lambda squared over 2 minus 1. So this should be minus 1. I'm taking them in order of minus r rho. The problem is that there are 2 sign conventions for Lorentzian lattices, and I always get them a bit muddled up. So this is norm 2, and this is the first batch of simple roots. So already we've got an infinite number of simple roots. And Conway made the amazing discovery that there are no more simple roots. And the reason there are no more is because lambda has covering radius less than or equal to the square root of 2. So Conway and Sloane's original calculation of the fact that the Leech lattice is covering radius root 2 was just this incredibly long calculation. They had to do, 50 pages of simply finding all the deep holes by brute force, and it looked like a bizarre coincidence that they all happened to have radius just root 2. The reason for this is that suppose VAB is simple. Then it has inner product at most 0 with all the simple roots lambda 1 lambda squared over 2 minus 1. So this is the condition of Vinberg's algorithm, that any 2 simple roots must have inner product at most 0. And if you turn this into the geometry of the Leech lattice, it turns out to say that lambda minus v over a squared is greater than or equal to 2 plus 2 over a squared, which is not possible because this is greater than 2, and the Leech lattice is covering radius at most. This is covering radius root 2, so there are no vectors v over a with this property here. So the fact that Leech lattice is covering radius root 2 gives you this amazing fact that the Dinkin diagram of the 26-dimensional Lorentzian lattice is the Leech lattice. So this kind of okay, I seem to have I was asked to give a break after 45 minutes, and it now seems to be about 65 minutes. What are we doing about breaks?
If you'd like, we can take a quick 5-minute break or so and continue for another, 20 minutes after the break, if you like.
Okay, so let's have a break for a few minutes to give everybody a chance to stretch their legs or whatever. I guess that doesn't apply on talk, whatever. You give me a chance to recover.
Yes, that's great. Well, we can first thank you for the first half. So thank you very much. And if there are questions during the break, people are welcome to discuss various things on their own.
Thank you, Richard.
I should say this isn't the first half. This is the first third of the talk.
Maybe we should extend. We should have an extended Vinberg
Well, whatever.
lecture series where you hear the other 2/3.
Okay, I'm just going to.
Sure. Why don't we reconvene at 1/4 after?
Yeah. Okay, so resume at 9:15.
Exactly. 12:15. Shall we resume with part 2?
Okay, yeah, sure. So the main result of the first part was Conway's description of the Dinkin diagram of the 26-dimensional even Lorentzian lattice, and I was saying that this kind of dominates the whole theory. Everything in lower dimensions seems to be follow from Conway's reflection group in 26 dimensions. So what I'm going to do now is to discuss Conway and Sloane's interpretation of Vinberg's results in terms of this 26-dimensional space. The point is, suppose we take a Dinkin diagram Dn contained in the root system of II25(1), which, as we saw, was just the Leech lattice in some sense. Then the orthogonal complement of Dn is just the even sublattice of I25 minus N1. And this was the lattice that Vinberg was working out the Dinkin diagram of. And Conway and Sloane showed that there's a very neat interpretation of Vinberg's Dinkin diagram. So the Dinkin diagram of this is just the points of lambda, points P of lambda, so that P union Dn is a spherical Dinkin diagram. So let's see how this works. Suppose you take, let's take Dn for n greater than or equal to 8. So here we have 1, 2, 3, 4, 5, 6, 7, 8. What we want to do is add an extra point to this in order that we still have a spherical Dinkin diagram. And there's only two ways of doing this. We can either add a point that isn't connected to anything, or we could add a point that's connected to just this point here. This then gives us a Dn+1 Dinkin diagram, and this gives us a Dna1 Dinkin diagram. And these vectors of the Leech lattice give us the norm 2 vectors of Vinberg's Dinkin diagram, and these ones give us the norm 1 vectors. So if you write down the Dn for n greater than or equal to 8 and find the appropriate vectors in the Leech lattice, you exactly get Vinberg's diagrams. Now let's look at what happens for smaller n. So for Dn D7, things are slightly different because now we can get a norm 1 vector, or, sorry, norm 2 vector, or we can get a norm 1 vector like this. But there's a third thing we can do. We can also add on a point here. This would give us an E8 Dinkin diagram. You see, we can't do this with D8 because that would give us an E9 Dinkin diagram, which isn't spherical. So these correspond to norm 2 vectors. These correspond to the norm 1 vectors. And these correspond to the norm 1 vectors R with RV congruent to VV mod 2. So you remember I said in the cases I 18.1 and I 19.1, we got a second batch of simple roots because a root could have even in a product with every vector of even norm. And it turns out these extra roots are caused, in this case, by the E8 Dinkin diagram. And something similar happens for D6. Here we get 1, 2, 3, 4, 5, 6. So this time we can again add on a point there, or we can add on a point here, or we can add on a point here. And these give you norm 2 vectors with this funny property here. And what happens next? Well, what happens for D6? So this is the case when Vinberg's algorithm kind of breaks down, or well, it doesn't actually break down, it just goes on forever. So let's take a closer look at it. So here we have, sorry, not D6, D5. 1, 2, 3, 4, 5. So here, as before, we can add a vector here and get norm 2, a norm 2 vector, or we can add a vector here and get norm 1, or we can add a vector here to get an E6 Dinkin diagram. And now something goes wrong because this gives us norm 3 vectors, and these are not roots. So, you know, if you do this, you sort of get a sort of Coxeter diagram, but it's not really a Coxeter diagram because some of the vectors enter norm 3 and aren't roots. And we can ask why do these things stop being roots at E6 when they were roots for E6 and E7 and E8? And the answer is the E6 Dinkin diagram has the following funny extra symmetry. See, it's got a symmetry like this. And this symmetry is called a sort of opposition involution. And it's given by taking -1 of the lattice times something in the reflection group. So the opposition involution of the Dinkin diagram, you write the automorphism -1 of the lattice as something in the reflection group times some symmetry of the Dinkin diagram. For E6, you happen to get something that's a non-trivial symmetry, whereas for E7 and E8, you get a trivial symmetry. And it's the problem is this opposition involution doesn't preserve the D5 inside it. You see, it maps this D5 to this D5. And it's the fact that this opposition involution doesn't preserve the D5 that causes this to no longer be a root. So this gives another explanation of why Vinberg's algorithm starts producing infinite Dinkin diagrams at I 21. So what's special about this? Well, the reason why we get 20 here is 20 is equal to the dimension of II 25.1 minus the dimension of E6. So this is an alternative explanation of why Vinberg's algorithm suddenly gives you infinite diagrams when you're looking at 20-dimensional hyperbolic space. It's to do with the dimension of E6 and the dimension of Conway's lattice. These two, so we've got two explanations. One is Vinberg's explanation saying you get lattices which don't have enough roots. And the other is Conway and Sloane's explanation, which says that it happens to be this dimension here. In fact, these two explanations are the same, because if you look at the two lattices Vinberg used, they had root systems A11, D7, and E6 cubed. Now, there are two Niemeyer lattices with root system E6 as part of their Dinkin diagram, which are A11, D7, E6, and E6 to the 4. And you see Vinberg's two lattices come from taking a Niemeyer lattice with an E6 component, and then you take a D5 in this E6 component and take its orthogonal complement, and that gives you one of these lattices used by Vinberg. So Vinberg's explanation really turns out to be the same as Conway and Sloane's explanation. They're slightly disguised forms of the same fact that, they're both caused by a certain embedding of D5 inside E6. If you go on further, let's look at D4. And Vinberg showed that again, in this case, if you take I21, 1, it has an infinite Dinkin diagram. But from Conway and Sloane's point of view, this seems to be a little bit odd, because let's take a look at what possibilities there are. Well, you can add a norm 2 vector there. So this gives us a Dinkin diagram A1D4. Or we can add a norm 1 vector by doing this. So here we get norm 1, and we get a D5 Dinkin diagram. Or we can add an E5 Dinkin diagram. So we can add a vector here and get E5, which is really the same as D5 if you look at it. Now, the problem is this gives us a norm 4 vector. And the problem is, if we now look at so here we've got E5, which is just D5, and here we've got the D4 in it, and E5 has an opposition involution, but you see that this opposition involution preserves the D4. So it should be a root by what I said before. So we seem to have a contradiction, because Vinberg showed that the Dinkin diagram of this lattice here was infinite, and it has an infinite group of symmetries. And on the other hand, we seem to have an argument saying that its Dinkin diagram should be finite and should have a finite group of symmetries. The resolution of this is that the orthogonal complement of D4 in I25-1 has a finite, does indeed have a finite reflection group, but this lattice, it contains I21-1 with index 2. So these two lattices aren't quite the same. One has index 2 inside the other, and this one has an infinite Dinkin diagram, and the reflection group is and its symmetry group is infinite, whereas this one just has a finite Dinkin diagram, and you can write down its finite Dinkin diagram just by taking all these sorts of vectors. Actually, there's another sort of vector. Of course, you can take these ones as well, but that just gives you something similar. This is actually sort of related to triality of D4. We notice that D4 has the root lattice D4 is contained in the lattice I4, but it's actually contained in 3 different copies. This is the famous triality symmetry of D4. And this turns out to be related here. You can see that this D4 has a triality symmetry where you can permute these three vertices, and that's why they're all sort of behaving in the same way. They all really correspond to roots. So I21(1) has the funny property that it's even sublattice. As finite Dinkin diagram. One of the most surprising things about hyperbolic reflection groups is, Euclidean and spherical reflection groups, you get reflection groups in every dimension. And you would expect the same thing to happen for hyperbolic reflection groups. But Vinberg showed there's an upper bound for the dimension of hyperbolic reflection groups with a finite volume fundamental domain. You can easily find reflection groups in any hyperbolic reflection groups in any dimension with an infinite volume fundamental domain. And some of these are even rather interesting. For instance, Conway's reflection group in 25-dimensional hyperbolic space has infinite volume fundamental domain. But I almost didn't believe this result when I first saw it. It sort of just goes against whatever intuition I had about hyperbolic space, which is there's lots of room to have reflection groups. Vinberg showed there actually isn't. This example here seems to be the largest dimension in which there is a hyperbolic reflection group with finite volume. So it's an open problem to find, is there a reflection group of finite volume fundamental domain in dimension larger than this? So the title of the talk said it was going to be Vinberg's algorithm and Kac-Moody algebras. So I'll just spend a few minutes talking very briefly about this. So if we've got a Dinkin diagram, this gives us a Lie algebra. For instance, if you take the E8 Dinkin diagram, this gives us the famous E8 Lie algebra. And the way you get this Lie algebra is each point gives you a copy of the Lie algebra SL2 of R. And the lines between points tell you the relations, how these little SL2Rs are embedded. For instance, if 2 points are not joined, the little 2 copies of SL2R commute. And if they're joined by one line, then the 2 copies of SL2R are kind of embedded like the 2 copies of SL2R inside SL3R. So here we've got 2 copies of SL2R and they kind of overlap. And single line joining them, they're sort of joined in this way. Now the spherical Dinkin diagrams give you finite dimensional Lie algebras, and Kac-Moody sort of pointed out that you can actually take any Dinkin diagram, it doesn't need to be spherical, and ask what Lie algebra do you get from it? Spherical Dinkin diagrams just give you finite dimensional Lie algebras. Euclidean Dinkin diagrams just give you the famous affine Kac-Moody algebras, which have been heavily studied by physicists. And then you can ask, what about hyperbolic Dinkin diagrams? These give you some Lie algebras, but it seems to be very hard to say anything about them. In particular, the root multiplicities seem to be rather complicated in general. Well, the obvious ones to look at are Vinberg's Dinkin diagrams of I n1 and I n1. And the most striking of these, not very surprisingly, turns out to be Conway's example. So let's take the Dinkin diagram of II 25, 1, which is equal to the Leech lattice. So we can make this into a Kac-Moody algebra just by taking the usual generators and relations, and we can ask what its root multiplicities are. Well, the roots can have the following possible norms. It can have norm 2 or 0 or -2 or -4 or -6 and so on. So what's going on here is its root lattice, and it's got some roots of norm 2 and some roots of norm 0, and it might have roots of norm -2 here and so on. So there's a lot of stuff going. The Lie algebra sort of mostly lives inside these two cones, although it's got a few bits sticking out of it in some sense. We can ask what are the root multiplicities. The root multiplicities of the norm 2 roots are easy. Those are just 1. 0, we get 24 or 0. Here we get usually 324. There are altogether 121 orbits of norm -2 roots, and 119 of them, the multiplicity is 324, and for 2 the multiplicity is less. And here the multiplicity is usually 3200, and sometimes a bit less. And if you look at these numbers, you may notice that they appear as the coefficients of 1 over delta q, which is 1 over q times the product of 1 minus q to the n 24. Plus 24 plus 324q and so on. And this fact that the root multiplicities are always at most equal to these coefficients was explained by Igor Frenkel, who pointed out that the no-ghost theorem of physics could be used to construct something with vector spaces of exactly this dimension. You could show that this Lie algebra was actually could be embedded inside that, and so you get this upper bound for the root multiplicities of this Kac-Moody algebra given by these coefficients here. There's a sort of rather intriguing relation between the Lie algebras that you get from some of Vinberg's reflection groups and the and coefficients of various modular forms. That was going to be the second half of this lecture, but I seem to have come to the end of the time allotted for this lecture, so I guess I better stop now.
Okay, well, we can all unmute, and thank you very much for the beautiful lectures. Thank you.
Thank you.
And we have some time for questions. Do you have a sense? I mean, you found this largest dimension 21 hyperbolic guy. Do you have any other guesses for where you might want to look if you were to try to find another one? Your record has stood for many decades now.
Well, if I knew anywhere else to look, I would have looked for things there. So no, I don't have any good ideas. I mean,
I guess it won't come from lattices over Z, because now we have Charlot's classification of those.
Yeah, and I think
or Esselman even.
Esselman sort of showed that it was certainly showed that this was the largest of some class of lattices. So yeah, maybe you'd have to look at lattices over other algebraic number fields. But people like Charlau have looked at those, and that they all seem to give you examples in dimensions less than what you get over Z. Yeah, I mean, it's one interesting open problem is can you find analogues of the Leech lattice in this 26-dimensional example over other number fields? You can do this in a few cases. So you can make the Leech lattice into a lattice over the Eisenstein integers, for example, and use that to do something over the Eisenstein integers. But I sort of still wonder, is there some sort of analog of Conway's, really striking reflection group for other number fields?
Yes, I wanted actually to leave a comment that indeed this example is still our world record for many decades. And yeah, there can be no other arithmetic non-compact reflection groups in higher dimensions. So this is indeed the sharp bound. As for compact ones, actually, Vinberg's algorithm also produced the current world record by Bugayenko. It was
you got some examples in about 8 dimensions, and
yes, in dimension 8.
I have another open problem about that. I've stared quite hard at Bugayenko's example, and I have this theory that everything in low dimensions you should be able to get dimensions. That's a sort of open problem. Is Bugayenko's example related to Conway's example? I think Bugayenko is almost the only example I know that doesn't somehow come from Conway's example.
I actually was trying to compute the infinite volume domains of lattices like minus roots of something plus dn with large n. I was trying to find this infinite volume fundamental domain and then computing the faces of some like lower dimensions. It's still I didn't find anything. I even wasn't able to find anything new in dimensions 7 and 8. So still those old examples are still records. It's amazing.
Yes, you can pick up quite a few examples similar to Conway's by basically by taking fixed points of the Leech lattice and then copying Conway's example. These were investigated by Peter Niemann several years ago. And they were partly classified by Neil Scheithauer, and I think there's actually a recent paper I think it's by Scheithauer and Wang, which classifies them under some conditions. You seem to only get a rather small number of examples, a dozen or so.
Yeah, so I remember what Nikolai and I did some time ago. We took this 21-dimensional polytope and tried to make our computer to go down in the face lattice and just compute all the faces and then faces of faces and so on. Of course, pruning this kind of tree that you get up to isometry and look for Coxeter faces. So for example, in dimension 20, you don't have Coxeter faces, right? Otherwise, you would have arithmetic reflection lattices there. But then in lower dimensions, you get something in dimensions 19 and 18, and these are exactly the Vinberg polytopes. And so it descends. Sometimes you go through non-Coxeter faces and then get Coxeter faces again. And I think so far we didn't find anything new. Like everything we found was somewhere in Alcock's papers and so on. So
yes, I had this problem that whenever I found something, it always turned out to be in one of Vinberg's papers. So you can, instead of taking the orthogonal complement of dn, you can try taking orthogonal, that gives you a lattice with reflection group of 3, but I thought I'd found something new, but then discovered Vinberg had already found this earlier. So Vinberg found nearly everything you can get, as far as I can figure out, at least in high dimensions.
I see Mamuka has a hand raised.
Yeah, I want to ask something, but before that, I would like to ask, Alex, you mentioned this possibility. Would it be possible that you give a second lecture at the seminar?
Yeah.
That would be great.
Yeah. Yes. Yeah. I could give the second half of this one.
Well, you don't have to answer now. We can discuss offline, and if you agree, we'll be happy to schedule it.
Yeah, sure.
Okay, so then I go
Actually,
on with
I mean,
my
yeah,
question.
I was thinking that the other thing I could do is just, I mean, we've been having some trouble with connections going down, so I could just record the lecture online and post it or something like that. And maybe that would be easiest.
If you'd like to do it that way, whatever you, yeah. Why don't we discuss over email and see what.
You cannot ask questions if it's online recorded.
That's true. That's true.
Is that a disadvantage or an advantage? I'm not quite sure.
So my mathematical question was, I mean, do people do something like bookkeeping of all those lattices in some structure, like, I don't know, some Grothendieck ring or Barside ring or something like that?
Are you talking about the Nemai lattice question? About
No, I mean all lattices together with some operations on them.
Yeah, you can do that. I mean, that the lattices have a perfectly good tensor product on them, which gives you a sort of, as you say, you can get a Grothendieck ring structure on, say, all unimodular lattices or all lattices. And people have thought about this a bit, and the trouble is it just goes absolutely crazy. The problem is the number of lattices in dimension n increases quite nicely up to about n equals 24 or n equals 25, but beyond that it increases more than exponentially fast. You know, that there are sort of, I think in dimension 32, even if you restrict to even unimodular lattices, there are more than 1 billion of them. So your ring is just going to be absolutely crazy. It's going to be a graded ring, but the dimension of the degree n piece is reasonable up to about dimension 24, but then goes utterly wild. So it's rather hard to see what you could do with it. I mean, it's just so big.
That's the shower picture, right? Remember from the picture of the number of unimodular lattices drawn as a shower, which explodes at above 25 dimensions.
Yeah. And the reason, I mean, that there's a reason why it explodes at 25 dimensions, and that is the Leech lattice is controlling everything up to 25 dimensions. So all, for instance, all unimodular lattices up to 25 dimensions can be sort of lattice if you look. But as soon as the Leech lattice stops controlling lattices, sort of everything goes totally wild. So that's the Leech lattice is the point where there's a phase change. And you know, there's a phase change once you go from below the dimension of the Leech lattice to above the dimension of the Leech lattice.
Misha, you have your hand raised.
Yeah, I have a quick question. So there was a paper by John McLeod where he looked at the hyperbolic reflection groups given by quadratic form -3 x 0 square plus 1 1 1 1 diagonal. So it's like very similar to Vinberg's examples, but one next. And he found the lattices up to dimension, I think, let me check, 15 or something. Oh no, 13. So I know that these examples were new to Vinberg this after dimension 10, and I wonder how they fit in the scheme. I mean, I believe they should fit, but I didn't check it, so maybe you know.
Well, yeah. What one question is, can you? I don't know. I mean, questions.
I
Can
can
you?
see the paper. There are diagrams there.
Yeah, it might be possible to. You can get some lattices by taking orthogonal complement of a DNE6 Dinkin diagram inside. You pick a D6. Sorry, an E6 D4 inside the Leech lattice and look at the orthogonal complement of that, and that will sometimes give you a determinate free lattice with a
I
finite.
forwarded the link just in case in the chat.
I don't know exactly how those tie up with his examples, though.
The thing is that the diagrams, you know, in dimensions over 10, they're quite nice and very symmetric as well. So
Yes. So let me see. E6 D4 would give you things inside a Lorentzian lattice of dimension 16. So my guess would be dimension up to 14 and dimension 16. You might get a finite Dinkin diagram, but
well, here it's actually up to hyperbolic dimension 13, but dimension of the quadratic space 14. So yeah. Well, anyways.
Yeah, I don't know. I have to do some calculation, and I'm just thinking off the top of my head.
Well, thank you.
This is a question from Christopher. Do you want to unmute and ask it, or would you like me to ask for you?
Yeah, I can ask it. Thanks. I was wondering, well, one is which lattices have deep holes at distance strictly less than 1? And the reason why I'm asking is because I'm wondering if one could develop a theory of continued fractions using a Euclidean algorithm,
Yes,
analog to the case of Euclidean quadratic rings.
Yes, as you say, this is sort of related to the Euclidean continued fraction algorithm in some sense. For lattices of covering radius 1, so the E8 lattice is covering radius exactly equal to 1, and the E8 lattice plays sort of the same role as the Leech lattice if you just look at roots of norm 1 rather than roots of norm 2 as for the Leech lattice. So you get a few lattices. You can get some lattices of covering radius less than 1 by hang on, it's a long let me see. Yeah, what's going on is you don't exactly want the lattices of covering radius exactly equal to 2, because when you take the fixed sublattice of the Leech lattice under an automorphism, you sometimes get something that is covering radius a little bit greater than 2, but you can cover it with spheres of 2 different sizes. Yes, sorry, I'm getting a bit off track. I think the short answer is I don't know off the top of my head how you get lattices of covering radius less than 1, but I've got a vague feeling you can do it by fiddling around with the Leech lattice a bit to get a few examples.
So in the spirit of what you were saying before, everything which is kind of controlled by the E8 lattice, like
yes,
would
the E8 lattice sort of controls things up to dimension 8 if you're talking about reflection groups that only have norm 1 roots.
So maybe that would suggest that the only ones come from units in the fields or non-commutative fields like Eisenstein, then Hurwitz integers, then and then for the octonion, some kind of integers in the octonions, and maybe these would be kind of all the examples. I mean, if it's I don't know, I'm kind of just guessing.
Yeah. My feeling is, the way to answer that question, I'd have to sit down and calculate for several days.
Okay, thanks. So
Just
it's
trying to
not
guess
obvious.
It's not obvious to me, but yeah, I'd start by looking at E8 and fiddling around with this in various ways.
Did you want to ask your other question, Christopher? About theta functions?
I'd like to ask.
That was not a question. I mean, it was just kind of naively suggesting, like, if you're looking for examples of lattices as before, then the counting function, like counting the number of vectors of each norm, its theta function, that should be, you expect it would be a modular form. So maybe using classifications of modular forms with the properties you would expect, maybe you can show that, well, we've already got all the modular forms, and then it's a matter of ruling out isospectral examples, and that may be more subtle, but I don't know. I was just
yeah. Well,
it's probably a naive idea.
No, there are some very deep connections between these reflection groups and various automorphic forms. That was going to be mentioned in the second part of the talk, but and one plan for trying to classify hyperbolic reflection groups was to associate an automorphic form to the hyperbolic reflection group, and then, as you say, try and classify the corresponding automorphic forms. This seems to be quite difficult to implement, though. I mean, there are certainly a lot of hyperbolic reflection groups that correspond to automorphic forms, but it's not clear how to see that all hyperbolic reflection groups correspond to automorphic forms.
I think we have time for just one more question. Jeff Ligarius, if you want.
I'd like to ask. Well, my question's first. It's a lovely talk. Thank you so much. It had to do when you were discussing the Conway-Sloan interpretation, where you were saying that the DNs are appearing inside the I don't know what it's called, 225.1.
Yes.
Are those the DNs for n less than 24, or is there no bound?
Well, you can't embed dn for n greater than 25 inside the Leech lattice.
Okay.
I mean, for dimension reasons.
Yes, that's
so it would be, you can do D4 all the way up to D25, although D25 isn't terribly interesting because its complement is just going to be a one-dimensional lattice, and if you can't figure out the automorphism group of that, trouble.
Thank you.
All right. Well, why don't we all thank Professor Borcherds for beautiful lectures, and maybe we'll have more later, but that's to be determined. So thank you very much.